Hello and welcome to the Quantum Slumber. Tonight, we're stepping into a part of science that's quietly everywhere, so close to you that it's easy to miss. Not the distant stuff, not galaxies, not black holes, but the hidden architecture of matter itself. Because here's the strange thing. Chemistry looks so familiar on the surface. We learn names for elements. We memorize patterns. We talk about bonds like little sticks between atoms, and reactions like ingredients in a bowl. And it works well enough to feel ordinary. But underneath that ordinary layer is something much more precise. A set of rules that doesn't behave like our everyday intuition. Rules that come in steps, not smooth slopes. Rules where allowed and forbidden are not metaphors, but literal boundaries. Rules that decide, silently, why a material shines, why another one stays dull, why some things conduct, why others refuse, why oxygen does something that still surprises people the first time they see it. And that's what quantum chemistry really is. It's not chemistry, but with harder math. It's chemistry's source code. The reason the periodic table isn't just a list, but a pattern that keeps repeating like a melody. The reason a molecule can have a signature, like a barcode made of light. The reason the same tiny building blocks can rearrange into perfumes, oceans, batteries, medicine, and the devices humming softly around you right now. So, as you settle in, let me ask you something I always love to know. Where are you listening from tonight? And what time is it there? A city, a country, a quiet room, whatever you'd like to share. And if you enjoy these slow, gentle science journeys, you can softly tap like, subscribe, and join us again. It helps the channel find the right kind of night owls, the ones who like their curiosity calm, and their questions answered without any rush. No pressure, no clutter, no need to keep up, just you. And the quiet truth that matter isn't quite what it feels like, and the closer we look, the more beautifully strange it becomes. At first glance, chemistry doesn't feel like it should belong to the quantum world. It feels smooth, predictable. You pour, you stir, you heat, you wait. A metal warms in your hand. A drop of dye spreads through water in a slow, graceful cloud. A candle flame keeps its shape, steady and familiar, as if matter is simply doing what matter does. And for most of everyday life, that's a perfectly good illusion. But chemistry becomes quantum the moment you ask a question that sounds almost too simple to matter. Why does a substance have this color and not any other? Why does one gas glow a thin, sharp red while another leans toward violet? Why do certain materials soak up light like a sponge while others throw it back at you as a clean, bright shine? If chemistry were purely continuous, purely smooth, those answers would be smooth too. You'd expect a gentle blur of possibilities, a rainbow without structure, a world where energy can slide to any value it wants, like a dimmer switch that never clicks into place. But the universe doesn't work like that. At the smallest scales, energy behaves less like a dimmer, and more like a staircase. Not because nature is being dramatic, not because scientists like complicated words, but because the things doing chemistry, electrons and nuclei, don't move through space the way marbles do. They follow rules that feel more like music than machinery. They can resonate, they can interfere, they can settle into stable patterns and refuse everything else. And that refusal is the beginning of quantum chemistry. Imagine you're trying to stand on a ladder in the dark. Your feet search for a rung. You can't place your weight halfway between rungs and call it stable. You either find a rung or you don't. Now, translate that idea into the microscopic world. Electrons can stand in certain energy states that are stable, and they can't in the in-between places. Those stable states are what we call energy levels. They're not a decoration in the theory. They're the reason matter doesn't collapse, the reason atoms have size, the reason chemistry exists as something reliable instead of chaotic. Here's the gentle twist. When an electron changes its energy, it doesn't drift there. It doesn't glide. It jumps, not in a cartoon way, but in a rule-bound way. It moves from one allowed level to another allowed level, and that change has a price tag. That price tag is a very specific amount of energy. And when that energy is paid or released using light, the light comes out with a very specific color. This is where the world stops being continuous and starts being signature-like. Because light is not just brightness, light is information. Light carries energy in packets, and each packet has a frequency, which we experience as color. When an atom or molecule absorbs light, it's not absorbing some light. It's selecting certain frequencies that match the gaps between allowed energy levels. It's choosing from a menu, and it's a menu with surprisingly sharp boundaries. That is why, when you send white light through certain gases, you don't get a smooth rainbow on the other side. You get lines, thin, bright stripes at very particular colors, like someone took a ruler and drew them into the spectrum with quiet precision. Those are spectral lines. They're the earliest, clearest hint that nature runs on discrete rules. That chemistry isn't just mixing and reactions, but a choreography of allowed and forbidden steps. Long before we had the modern language for orbitals and wave functions, those lines were already telling the truth. Scientists could look at the light from hydrogen and see a pattern that refused to be random, a pattern that kept repeating, like a phrase of music returning in a different key. And in a way, that's what a spectrum is. It's a fingerprint made of light. Every element has its own. Every atom, with its own spacing of energy levels, will absorb and emit at its own unique set of frequencies, which means you can identify an element from far away, across a lab bench, across a city, across space, just by reading the light it gives you. Chemistry becomes quantum because the inside of atoms is not hidden. It's constantly leaking clues into the world as light, and those clues are embarrassingly specific. If matter were classical, you could heat something up, shine light on it, and expect a broad smear of outcomes. Instead, atoms answer like disciplined instruments. This note, not that one. This jump, not that jump. This line, not a blur. Now, there's a subtle reason this matters for chemistry specifically. Physics can talk about a single particle and call it a day. Chemistry can't. Chemistry is about crowds. It's about electrons sharing space, tugging on one another, arranging themselves into patterns that become bonds, shapes, reactivity, stability, scent, taste, and life. So, the moment you admit energy is quantized, stepped, you also admit something bigger. Matter has an internal architecture, not a metaphorical one, a real one. A set of allowed structures that determine what matter can be and what it can never be, no matter how much you wish it would behave. This is why certain reactions happen readily and others feel stubborn. This is why molecules have preferred shapes. This is why a material can be transparent or opaque, brittle or flexible, reactive or inert. The classical picture can describe the surface behavior, but it can't explain the stubborn precision underneath. Quantum rules can. And maybe the most calming thing about this is how consistent it is. The quantum world has a reputation for being weird, and it is, in the way a dream is weird when you look too closely. But it's also unbelievably dependable. The same rules that shape a sodium flame into that unmistakable yellow are the same rules that make lasers possible, make modern screens possible, make so much of our technology quietly ordinary. And they do it without opinion. Without hesitation, just rules. When you're sitting with a cup of tea and you look at the color of the liquid, you're not just seeing brown, you're seeing a filter, a selection, a set of allowed absorptions, molecules inside that drink, choosing which parts of the spectrum they keep and which parts they send back to your eyes. When you look at a leaf and see green, you're seeing a decision made by quantum levels. Certain photons are welcomed, others are refused. That refusal becomes color. Even smell, in the broadest sense, is about structure. And structure is about how electrons settle into stable patterns, and how those patterns interact with other patterns. So, chemistry becomes quantum, because chemistry is not actually about stuff. It's about states, stable arrangements, allowed configurations, energies that come in steps, and transitions between those steps that show up as light. Light that can be measured, decoded, and trusted. Once you see it that way, Spectra stop being an abstract graph in a textbook. They become one of the most intimate messages matter can send you. You shine light, and matter answers. Not with words, not with feelings, with a signature. A set of lines and gaps that says, this is who I am, this is what I allow, this is what I cannot do. And that's the quiet doorway into quantum chemistry. Because from here, the story naturally tightens. If energy levels exist, then there must be a reason they exist. There must be rules that create them, rules that shape where electrons are allowed to be and how they're allowed to behave. And those rules don't just explain spectra. They explain the rest of chemistry's personality. So keep just one gentle thread in your mind as we move forward. Levels become rules, and rules leave fingerprints. When most people hear the word orbital, they picture something tidy and mechanical, little electrons looping around a nucleus like tiny planets. It's a comforting image because it feels familiar. It feels like the kind of motion you could trace with your finger. But the real story is gentler and stranger. An orbital isn't a path. It's not a track in space. It's closer to a rule about where an electron is allowed to be, where it can settle into a stable pattern without the whole atom becoming restless. If you want a simple mental picture, think of an orbital as an allowed shape of probability, a three-dimensional region where an electron is likely to be found if you go looking. Not because the electron is hiding there like a marble in a box, but because the wave-like nature of the electron has formed a standing pattern, the way a violin string forms stable vibrations only at certain notes. That's the quiet leap quantum chemistry makes. Matter is not built from tiny balls following tiny roads. Matter is built from stable patterns, and those patterns come with rules that create the periodic table. So, let's keep it calm and clear. If we understand orbitals as allowed patterns, then the periodic table stops being a list you memorize in school and becomes something more like a map of habits. The atom's quiet architecture. Inside every atom, two things are always happening at once. There is attraction, the nucleus pulling electrons inward, and there is structure, the electron refusing to collapse, because it isn't a classical object. It behaves like a wave, and waves don't like being squeezed into nothing. When you confine a wave, you force it into higher energy patterns. The electron pushes back against being pinned too tightly, not out of stubbornness, but because confinement has an energetic cost. So, the atom becomes a compromise. Not a messy compromise, an elegant one. Electrons arrange themselves into orbitals, stable probability shapes that fit the nucleus's pull without paying unnecessary energy. That's why orbitals come in families. The simplest family is called S. These are roughly spherical because the simplest stable shape around a center is symmetry, no preference for direction. Then come p orbitals, which look like two lobes, like a soft dumbbell shape, because the next stable patterns have a directional character. They're still standing waves, but now with a kind of north-south personality in space. Then come d and f orbitals, more complex shapes, like the higher harmonics on a string, patterns that only appear once the simpler seats are already taken. And that word taken matters, because electrons aren't just drifting into these shapes one by one, as if the atom is a hotel with unlimited keys. There's a strict occupancy rule, one of the most important rules in all of chemistry, the Pauli exclusion principle. In plain language, electrons don't like sharing the exact same quantum identity in the same place. In an orbital, you can fit two electrons comfortably, but only if they differ in a particular quantum property we call spin. You can picture it like two people sharing a narrow bench. It works only if they sit in opposite orientations. So each orbital holds up to two electrons. That's it. And suddenly the periodic table begins to form, not as a human invention, but as a natural consequence of filling rules. Filling is destiny. Think of an atom building itself the way a quiet room fills with people. The first people choose the easiest seats. That's the 1s orbital, the lowest energy, closest to the nucleus. Two electrons fill it, and the room feels balanced. Then the next available seats appear, 2s, then 2p, then 3s, then 3p, and so on. Already, you can hear the rhythm: shells, subshells, orbitals, each with limited capacity. The ordering is not arbitrary. It follows energy costs and the shapes available. Now here's where chemistry becomes almost poetic. An element's personality, its reactivity, its bonding behavior, its tendency to donate or grab electrons, comes mostly from a single idea. What's happening in its outermost orbitals? Those outer electrons are like the edge of the atom's influence. They're the ones that feel the environment. They're the ones that touch other atoms first. They're the ones that get traded, shared, or rearranged when chemistry happens. So, when you look at the periodic table, you're not looking at a catalog of substances. You're looking at repeating patterns of outer electron arrangements. That's what makes it periodic. Not time, not a calendar. A repeating rhythm of quantum architecture. Why the rows repeat? Start with hydrogen, 1 electron. It sits in 1s. Helium, 2 electrons. 1s is filled. The first level is complete, stable, content. Then lithium arrives. It has 3 electrons. The first 2 go into 1s because that's the lowest seat. The third one has to go somewhere else, so it goes into 2s. That single outer electron changes everything. Lithium becomes eager to lose that outer electron, because if it does, it returns to the stable helium-like arrangement underneath. That's why alkali metals are reactive. They have this one lonely outer electron that they'd rather not carry around. Now move across the row. Beryllium has 2 outer electrons and 2s. Boron starts filling 2p. Carbon fills more. Nitrogen, oxygen, fluorine. Each step across the row adds an electron to the outer layer, and the desire of the atom shifts. Early in the row, elements tend to donate electrons to reach a stable previous configuration. Late in the row, they tend to accept electrons to complete their outer orbitals. Then you reach neon. Its outer shell is full. 2s and 2p are complete. Neon is famously unreactive because it has no incentive to change. Its architecture is already closed and stable. And then the next row begins and the whole pattern repeats, but on a larger scale. That repetition is the heartbeat of the periodic table. So, when you see columns, groups, those are families of elements that share a similar outer electron arrangement. Similar arrangement means similar chemistry. Similar chemistry means similar bonds, similar reactions, similar tendencies in the world. This is why sodium behaves a lot like lithium, why chlorine behaves like fluorine, why noble gases sit on the far right like calm sentinels. Their outer layers are already complete. It's not magic, it's orbitals. The table isn't a list. If you were forced to summarize the periodic table in one sentence, you could say, it's a visual record of how electrons fill orbitals. That's why the table has the shape it does. The 2 columns on the far left are dominated by s orbitals. They're the simplest seats, filled first in each row. That's the s block. The 6 columns on the far right are the p block, where the p orbitals fill and chemistry gains strong directionality, because p orbitals have direction, and that direction influences bonding and shape. And in the middle sits the d block, the transition metals, where those d orbitals come into play. This is where chemistry becomes wildly rich. Multiple possible oxidation states, colorful compounds, complex catalysis, magnetism, and more. Not because the elements are special, but because the d orbitals create more ways for electrons to distribute themselves. Then at the bottom, you have the f block, where even more complex orbitals fill. Rare Earth behavior, subtle magnetic and optical properties, a kind of fine-grained quantum personality. The table's layout is a diagram of orbital filling, which is why that click line is true. The table isn't a list, it's a map of allowed quantum habits. Orbitals as chemistry's grammar. Once you really accept orbitals, chemistry stops feeling like a collection of unrelated facts and starts feeling like a language with grammar. Why does carbon make 4 bonds so reliably? Because its outer orbitals can arrange into a bonding pattern that encourages that behavior. The shape and availability of orbitals makes the common bonding patterns not just possible, but natural. Why do halogens love to grab one electron? Because their outer orbitals are one electron short of a stable completion. Why do noble gases keep to themselves? Because their outer orbitals are already filled, and changing that costs energy without offering stability in return. You can think of orbitals as the sentence structures matter prefers. Atoms don't want anything emotionally, of course, but they do drift toward arrangements that lower energy and increase stability. Orbitals determine which stable arrangements are even allowed to exist. And that is where chemistry's predictability comes from. Not from human labels, from quantum permission. A calm way to picture it. If orbitals still feel too abstract, here's a softer way to hold it. Imagine each atom is a small, invisible concert hall. The nucleus is the stage. The electrons are not little musicians walking around. They're more like the sound in the hall, vibrations that can only form stable patterns at certain resonant shapes. Those shapes are orbitals. Some are simple and round, like a low note that fills the room evenly. Some have lobes, directional, like a note that emphasizes certain regions of the hall. Some are intricate with nodes, quiet zones where the probability goes to almost nothing, because standing waves always have places of silence. And because the hall has rules, you can't pack infinite sound into the exact same pattern. You can fit 2 electrons per orbital because of this opposite spin arrangement, but after that, the hall forces you into a different resonance. Now expand that image. Different atoms have different hall sizes and different pulls from the stage, which changes the energies of the resonances. But the pattern of filling, lowest first, 2 per orbital, repeating families, remains. That repeating structure is what you see when you look at the periodic table. And the moment you see it, the table stops being a chart. It becomes a story about structure, the bridge to what comes next. Orbitals in the periodic table give you the rules. They tell you what kinds of electron patterns are allowed, and why certain chemical behaviors repeat like familiar themes. But chemistry doesn't stay inside single atoms. Chemistry begins when orbitals meet orbitals, when 2 atoms come close enough that their allowed probability shapes start to overlap, negotiate, and sometimes merge into shared arrangements. That's where bonds come from. Not from little hooks, not from glue, from quantum shapes making compromises. And sometimes, just sometimes, those compromises reveal something surprising enough to feel like a small mystery. A clue that the orbital picture isn't just useful, it's real. Picture a simple question that sounds almost childish, and somehow refuses to stay simple. If atoms are mostly empty space, and electrons are not little marbles but cloudy quantum patterns, then what does it mean for 2 atoms to stick together? What is a chemical bond, really? Most of us grew up with the cartoon answer: atoms have little hooks, and they clasp hands. Or they share a pair of electrons like a neat little agreement. It's a useful picture. It gets you through a test. But if you stay with the real physics for just a little longer, the bond becomes something quieter and far more elegant. A bond is not a piece of glue. A bond is a solution. It's a stable arrangement the universe allows when electron waves overlap and reorganize in a way that lowers the total energy. It's a kind of peace treaty between competing forces, attraction and repulsion, confinement and freedom, order and uncertainty. And tonight, we're going to treat bonding like a small mystery story, because there's one everyday clue that makes the whole case feel unmistakably real. Oxygen. The same oxygen you breathe is, in a very specific way, weird. It gets pulled into a magnet. Not because oxygen likes magnets the way iron does, but because deep inside its electron arrangement, there are unpaired spins that refuse to disappear. That one fact is a fingerprint at the crime scene, and it forces us to take bonding seriously as quantum mechanics, not as a cartoon. The quiet problem bonds solve. Let's begin with the tension. Every atom is an arrangement that already took work to become stable. The nucleus pulls, the electrons settle into orbitals, allowed shapes of probability. Now bring 2 atoms close. Immediately the situation becomes crowded. Nuclei repel each other because they're both positively charged. Electrons repel each other because they're both negative. If that were the whole story, atoms would never cooperate. But there's also attraction. Each nucleus pulls on the other atom's electrons, and the electrons, those wave-like patterns, can spread out over both atoms instead of staying confined to one. Spreading out matters because confinement costs energy. A wave squeezed into a small region has a kind of restless intensity. Give it more room and it can relax into a lower energy pattern. So bonding often begins with a gentle idea. If electron probability can spread over a larger region, the system's energy can drop. And whenever energy drops, stability rises. That's the origin of many bonds. Not a handshake, but a shared wave. Two ways to tell the same truth. Chemists have two classic storytelling styles for bonds. They're not enemies, they're different camera angles on the same scene. Valence bond theory, VB, tells the story like a relationship. Two atoms share a pair of electrons between them. Overlap the orbitals, pair the spins, form a bond. It's local, intuitive, and it matches the way we draw Lewis structures. It's the language of, this bond is here between these two atoms. Molecular orbital theory, MO, tells the story like a weather system. Instead of electrons belonging to one atom or the other, they belong to the whole molecule. The orbitals themselves combine into new orbitals that spread across both atoms. These orbitals can lower energy, bonding orbitals, or raise energy, anti-bonding orbitals. It's more global, more wave-like, and it naturally explains some phenomena that VB struggles with. If VB is a close-up of hands clasping, MO is the wide shot of the entire dance floor. Both are describing quantum reality. They're just choosing different metaphors and different approximations. And oxygen, the magnet clue, leans hard toward the MO perspective, because it's really about how electrons arrange across a whole molecule. At the simplest bond, one molecule, two atoms. To feel the difference, it helps to start simple. Imagine two hydrogen atoms drifting close. Each has one electron in a 1s orbital. When the atoms approach, those two 1s orbitals overlap. In MO language, they combine into two new orbitals, a bonding orbital where the waves reinforce each other between the nuclei, concentrating electron probability in the region that can hold the nuclei together. An anti-bonding orbital where the waves cancel between the nuclei, leaving a node, a low probability region right where you'd want electrons to stabilize the bond. One of these lowers energy, one of these raises energy. If the two electrons occupy the lower energy bonding orbital with opposite spins, the total energy drops compared to two separate atoms. That energy drop is the bond. And that's hydrogen gas, H2. VB tells this as they share a pair. MO tells this as electrons occupy the bonding molecular orbital. Same truth, different lens. Now keep that structure in your mind because oxygen will take the same idea and complicate it just enough to reveal something strange. What bonding and anti-bonding really mean? The words can sound dramatic, like the orbitals are morally good or bad. But it's simpler than that. In a bonding orbital, electron probability is enhanced between the nuclei. That negative charge sitting between two positive nuclei helps reduce nuclear repulsion and effectively binds them together. In an anti-bonding orbital, electron probability is reduced between the nuclei. Often there's a node, like a forbidden quiet zone. That means less electron density to stabilize the nuclei, and the energy rises. So, bonds form when electrons can occupy more bonding than anti-bonding orbitals. This is why molecules have something like bond order, an accounting measure in MO theory. Bond order equals open parenthesis. Bonding electrons minus anti-bonding electrons. Close parentheses divided by 2. Again, it's not a mystical number. It's a way to summarize how much net stabilization the shared orbitals provide. Now it's oxygen. The oxygen case file. You've probably seen oxygen drawn as O equals O, a double bond. Two oxygen atoms sharing two pairs of electrons. If you look at that drawing, you might assume oxygen is quiet and fully paired, no loose ends. But oxygen in its ordinary form, O2, is paramagnetic. That means it is attracted to a magnetic field. Not strongly like iron, but noticeably. Enough that in demonstrations, liquid oxygen can be held between the poles of a magnet, suspended as if gravity briefly forgot its job. That is not a trivial detail. Paramagnetism usually means one thing: unpaired electrons. Unpaired electron spins create tiny magnetic moments. When you place them in a magnetic field, they tend to align in a way that produces attraction. So, if O2 is paramagnetic, it must contain unpaired electrons. But the basic VB double bond picture tends to pair everything up neatly. It doesn't naturally predict two unpaired electrons in ground state oxygen unless you add extra layers of explanation. MO theory, on the other hand, predicts it almost effortlessly. That's why oxygen is such a famous twist in chemistry education. It's a moment where the universe basically hands you a receipt. It's saying, yes, these orbitals aren't just math. They show up in real, measurable behavior. So, let's walk through the oxygen orbitals in a calm way. No clutter. How oxygen's molecular orbitals fill. When two oxygen atoms come together, you don't just combine two 1s orbitals. You combine their valence orbitals too, 2s and 2p. The 1s orbitals are deep and mostly irrelevant to chemistry. They're core electrons, tightly bound. The action is in the 2s and 2p. Each oxygen atom has 6 valence electrons, 2s squared 2p to the 4th power. 2 oxygens give 12 valence electrons to place into molecular orbitals. In MO theory, these combine into a ladder of orbitals, some bonding, some antibonding, with different energies. You fill them from lowest energy upward, following Pauli's principle, max 2 per orbital with opposite spins. And Hund's rule, within a set of equal energy orbitals, electrons prefer to remain unpaired with parallel spins as long as possible. That last rule, Hund's rule, is the quiet key to the magnetism. Because in oxygen, when you get near the top of the filling order, there are 2 orbitals of the same energy. The electrons spread out, one in each, unpaired before they pair up. And those 2 unpaired electrons remain in the ground state. That's the twist, not a special exception. Just the natural consequence of the orbital energy structure and the rules of filling. So, oxygen ends up with 2 unpaired electrons in what are often called the p antibonding orbitals, pi star. The star indicates antibonding. 2 unpaired electrons in antibonding orbitals might sound like it should weaken the bond. And it does, compared to what you'd get if everything were paired into bonding orbitals. But oxygen still has a net bond order of 2 in MO theory, which matches the double bond intuition. There are more bonding electrons than anti-bonding electrons. The net stabilization is consistent with a double bond. Yet the unpaired electrons remain, creating paramagnetism. So, the story becomes beautifully consistent. Oxygen is a double bond, and it has unpaired electrons. You don't have to choose one truth. MO theory gives you both. Why VB and MO both matter. At this point, you might wonder, if MO explains oxygen's magnetism so cleanly, why even keep VB around? Because VB is often the fastest way to think about local bonding and chemical structure. When you're predicting the shape of a molecule, thinking about hybridization, drawing mechanisms, following electron pairs, VB-style thinking is incredibly useful. But MO gives you something. VB sometimes hides. Delocalization, global electron distribution, magnetism, excited states, bonding patterns that are spread across an entire molecule. So it's not one is correct and the other is wrong. It's one is a close-up sketch and one is a full-field portrait. And oxygen reminds you that the full-field portrait is real. The magnet is the measurement moment. Here's the part that feels almost like an experiment you could do at home. You can't see orbitals directly, not with your eyes, not like a photograph. But you can see consequences. A magnetic field is, in a sense, a question you ask matter. Do you have unpaired spins? Oxygen answers yes, and it answers without drama. It answers with a subtle pull. That's the kind of moment that makes quantum chemistry feel less like advanced textbook stuff, and more like hidden architecture, the quiet framework underneath ordinary reality. Because oxygen is everywhere. It's in the air right now, it's in your bloodstream, it's in the chemistry of fire, rust, metabolism, and inside that everyday molecule, the quantum rules are sitting there, unbothered, doing their work. Bonding is compromise, not certainty. One more gentle point before we leave the oxygen case. It's tempting to think bonds are rigid, like you form a bond, and now it's locked in. But bonds are more like stable patterns that persist because they're energetically favorable, not because they're physically nailed together. That's why bonds can stretch, vibrate, bend. That's why molecules have spectra. They absorb and emit light at specific frequencies because their bonds are quantized in how they can move. Bonding creates structure, but it's a living structure, a dynamic one. And the same MO idea, bonding and anti-bonding orbitals, also explains why bonds can break. If you pump energy into a molecule, heat it, shine light on it, you can promote electrons into anti-bonding orbitals. You don't have to tear the bond like a rope. You can simply change the occupancy of orbitals, and the balance of stabilization shifts. A bond breaks when the orbital arrangement no longer favors togetherness. Again, not glue, a balance, a clean recap without repeating the world. So, what have we earned here? We started with a quiet question. What does it mean for atoms to stick? And the answer wasn't a hook or a handshake. It was a quantum reorganization. Electron waves overlap. New orbitals form across the molecule. Filling those orbitals can lower total energy. That energy drop becomes stability. And oxygen gives you the memorable twist. O2 is attracted to a magnetic field. That means unpaired electrons. MO theory predicts two unpaired electrons in the ground state. The bond is still effectively a double bond, but the spins remain unpaired, which is why oxygen is such a perfect viral block in a calm science story. It's surprising, it's testable, and it makes the theory feel unavoidable. And once you see bonding this way, chemistry starts to feel less like memorization and more like the universe expressing stable patterns. From here, the next natural step is to watch those patterns change. Not just in a static bond, but along a path. Because when molecules transform, they don't teleport from reactants to products. They move across an energy landscape, pass through a narrow high point, and sometimes get help finding an easier route. A bond isn't the end of the story. It's the starting geometry for motion. If bonding is the quiet agreement that lets atoms stay together, then a chemical reaction is what happens when that agreement changes. And from the outside, reactions can look almost magical. You mix two clear liquids and they suddenly turn warm. You strike a match and a solid becomes light. You leave a nail in the rain and day by day, the surface becomes something new. It's tempting to imagine reactions as simple before and after snapshots. Reactants on one side, products on the other. Like the world just flips a switch. But quantum chemistry asks you to picture something gentler and more honest. A reaction is not a switch. It's a journey across a landscape. Not a landscape you can hike with shoes and a backpack, but an invisible terrain made of energy, shaped by electron clouds and nuclear positions. A terrain with valleys, ridges, narrow passes, and a few steep places where almost nothing wants to linger. If you hold that image, molecules moving through an energy landscape, then a lot of chemistry suddenly becomes intuitive without becoming simplistic. Why some reactions happen quickly, why others want to happen but barely start, why heat helps, why light helps, why sometimes a tiny amount of a third substance changes everything without being used up. That third substance is the catalyst. And in the landscape picture, a catalyst does something very specific. It doesn't change where the valleys are. It changes which path you take to get from one valley to another. The valley you start in, imagine the reactants as resting in a low valley. That valley is stable in the ordinary sense. The electrons are arranged in a pattern that works. The bonds have settled into their preferred orbitals. The whole system, if you leave it alone, can remain that way for a long time. Now imagine the products as a different valley, sometimes lower, sometimes higher, sometimes nearly the same height. Chemistry textbooks will say, Products lower than reactants means the reaction releases energy, exothermic, like combustion. Or, products higher than reactants means the reaction absorbs energy, endothermic. That's true as far as it goes. But here's the part that actually controls whether anything happens tonight, in the real world, in your kitchen, or in your bloodstream. Between the two valleys, there is usually a hill. Not an optional hill, a necessary hill. And the height of that hill is the activation energy. The hill in the middle, if reactants are already allowed to become products, why do they need a hill at all? Because to rearrange bonds, the molecule has to pass through a moment where the old bonds are weakening and the new bonds aren't fully formed yet. That in-between configuration is unstable. It's a kind of tightrope moment where electrons are being asked to reorganize rapidly while nuclei shift positions. Quantum mechanically, this is where electron density is being redistributed in a way that temporarily raises the system's energy. The old stabilizing orbital patterns are partially undone before new stabilizing patterns take their place. So, the system must pay energy to reach that in-between point. That payment is the activation energy. And the top of the hill, the highest point along the easiest path, is called the transition state. The transition state is not a place you live. It's a place you pass through. It is the blink between was and becomes. If you could freeze time and look at that moment, you'd see a structure that looks almost like the product and almost like the reactant, but not comfortably either. Bonds drawn as dotted lines in chemistry diagrams. Distances half formed. Electrons in a distribution that feels temporary, like a breath held too long. Because it is temporary, the transition state is so fleeting that it's not a molecule in the normal sense. It's a peak on the energy landscape, an event, not a stable thing. And that's why reactions depend so strongly on temperature. Heat isn't energy for the products. Heat is energy to climb the hill. When you warm a system, you increase the fraction of molecules with enough energy in that moment to reach the top. Not all molecules, not even most sometimes, just enough that the reaction becomes noticeable. Now, the quiet meaning of rate. This is why the rate of a reaction can be slow, even when the reaction is energetically favorable. A reaction can have products much lower in energy than reactants, and still proceed at a crawl, because the hill is tall. This is one of the most important emotional truths in chemistry. A reaction can want to happen, and still not happen quickly, because chemistry is not governed only by where you end up. It's governed by how hard it is to get there. The landscape is destiny, and the hill is the gatekeeper. So, when we talk about kinetics, reaction speed, we're talking about that gatekeeper. A tall hill means only a tiny fraction of molecules are able to cross at any given time. A short hill means many can cross. A reaction that is instant is usually just a reaction with a low barrier and a pathway that is easy to access. One reaction, many possible paths. Now here's where the landscape image becomes even more powerful. A landscape is not a single line, it's a surface. And on that surface, there can be multiple routes between the same two valleys. One route might be steep and direct. Another might wind around and be gentler, even if it takes more steps. The important thing is that, in chemistry, steps aren't moral. The system doesn't mind taking extra intermediate arrangements if the highest point along the way is lower. This is the key idea behind catalysis. A catalyst provides an alternate route. The starting valley and ending valley remain the same. The reactants and products are still what they are. The total energy difference between them doesn't change. What changes is the height of the hill you must climb. That's why catalysts speed up reactions without shifting the final equilibrium position. In the way many people imagine, they don't make products more favored. They make the journey easier in both directions. A catalyst lowers the activation energy for the forward reaction and lowers it for the reverse reaction as well. It doesn't tilt the landscape. It carves a pass through the mountain. What a catalyst actually does, if we keep this strictly honest and still gentle, the catalyst works by changing how electrons and nuclei interact along the pathway. A catalyst might hold reactants close together in the right orientation, stabilize a developing charge in the transition state, offer a temporary bonding site that weakens a bond at the right moment, Provide an alternative mechanism with different intermediate structures. Distribute electron density in a way that makes rearrangement less expensive. All of those are different ways of saying the same thing. It makes the transition state less high energy. Sometimes that's by making the transition state itself more stable. Sometimes it's by creating a different transition state that is simply lower. Either way, the top of the hill becomes less intimidating, and the reaction rate can explode, sometimes by factors of millions or more, without changing the reactants or products. That's why catalysts feel like cheating, but they're not. They're just geometry and quantum rules applied with precision. A familiar example, the orientation problem. One quiet reason reactions can be slow is simply that molecules collide in unhelpful ways. Imagine two reactants as oddly shaped pieces that need to meet at the right angle. Most collisions aren't perfect. They glance off, or bump in the wrong place, or arrive with the wrong relative orientation for electron density to reorganize smoothly. A catalyst can act like a stagehand in a theater, placing two actors under the right light, in the right positions, at the right moment. In enzyme catalysis, this becomes almost literal. Enzymes have active sites shaped to bind substrates in specific orientations, reducing entropy cost and guiding electron transfer steps. Even non-biological catalysts can do a similar thing through surfaces, binding sites, or coordination to metals. The catalyst is not shouting new instructions at the laws of physics. It's quietly arranging the scene so the laws of physics do what they already know how to do. Enzymes, catalysts you are made of. If you want a moment where this all stops being abstract, think about your own body. At your body temperature, many reactions that could happen are painfully slow. Life needs speed, so life uses catalysts, enzymes, everywhere. Enzymes are not magic. They are catalysts made of protein and sometimes RNA that lower barriers by stabilizing transition, states, aligning substrates, and offering temporary chemical assistance. A useful way to say it is, enzymes are not designed to love the reactants. They are shaped to fit the transition state. That's why enzymes can be so specific and so fast. They make the highest point along the route feel less costly. They are landscape engineers. And you are living proof that catalysis is not a niche concept. It's the difference between chemistry that could happen and chemistry that actually happens in real time. Catalysts don't get used up, but they do participate. There's one subtle point that matters for intuition. People often hear, a catalyst isn't consumed, and imagine it as a bystander, floating nearby like a supervisor. But many catalysts take part in intermediate steps. They may temporarily bond to reactants, form intermediate complexes, and then be regenerated at the end of the sequence. So, the catalyst can be involved, deeply involved, without being consumed overall. It's like a key that turns inside a lock. The key interacts. It does work. But when the door opens, the key is still the key. Catalysts often cycle. That cycling is part of how they provide an alternate route through intermediate states that wouldn't exist otherwise. The landscape is drawn by electrons. Now, because this is quantum chemistry, we should give the landscape the respect it deserves. This energy landscape isn't arbitrary. It comes from the underlying quantum mechanics of electrons and nuclei. As atoms move relative to each other, the electron wave functions adjust. The distribution of electron density changes. The balance of attraction and repulsion changes. And the energy landscape is essentially a map of those changes. This is why chemists can talk about potential energy surfaces, reaction coordinates, and transition states with such confidence. They're not inventing a metaphor. They're summarizing the output of quantum calculations and experimental measurements. The hill is not just a story device. It is encoded in the physics, and catalysts alter that physics locally by changing electron distribution and stabilizing certain arrangements so the surface is reshaped. Not globally, not in the endpoints, just where the climb used to be steep. Why catalysts feel like they choose a route. Another way catalysts become powerful is selectivity. Sometimes there are multiple product valleys that are possible. The same reactants could rearrange in more than one way, leading to different products. A catalyst can favor one pathway by lowering the barrier for that particular route more than others. So it doesn't just speed up a reaction, it can steer chemistry. This is why catalysts are central to industrial chemistry, pharmaceutical synthesis, and biological regulation. They don't merely accelerate, they guide. And again, in the landscape picture, this is simple. If you carve one mountain pass much lower than the others, travelers will take it. A gentle pause. What this changes in how you see reactions. Once you internalize the landscape idea, you start noticing it everywhere. Why refrigerated food spoils more slowly? Lower temperature means fewer molecules can climb activation barriers. Why some reactions need light? Photons can promote electrons into states that open new pathways or lower barriers in a different way. Why a tiny pinch of platinum can make hydrogen and oxygen react dramatically faster. Why your body can run complex chemistry at mild temperatures without burning itself up. Enzymes lower the hills. And perhaps most importantly, you stop thinking of reactions as events and start thinking of them as probability flowing along the easiest path available. That's a very quantum way to imagine chemistry. Calm, statistical, and deeply physical. The catalyst's promise in one clean sentence. A catalyst doesn't change the destination. It changes the climb, and that's the difference between a reaction that is possible in principle and a reaction that happens in practice. A soft handoff without stepping on the next section. There's one more quiet connection here that will matter later. If reactions are journeys across energy landscapes, then the landscape itself has a kind of hidden signage. Molecules can reveal their internal energy spacings. They can reveal which motions and rearrangements are allowed. They can reveal the fingerprints of their quantum structure. And one of the most beautiful ways they do that is by interacting with light, absorbing certain colors, emitting others, responding with a pattern that looks almost like a barcode. Not because light is special, but because light is a question matter can answer with precision. There's a quiet way to learn what a molecule is without ever touching it. You don't need to break it apart. You don't need to weigh it or taste it or guess. You can simply ask it a question. And in quantum chemistry, the cleanest question we know how to ask is made of light. A beam of light moves toward a sample, gas, liquid, solid. It doesn't really matter, and something subtle happens. The molecule doesn't talk in words. It answers in permission. It keeps some colors. It refuses others. It takes a little energy at very specific amounts, and then gives it back in its own time, in its own shape. That response, this pattern of allowed and forbidden energies, is what we call spectroscopy. But the word can sound colder than the thing itself, because what spectroscopy really means is, you shine light and matter answers. And the answer is not vague. It's a barcode, a fingerprint, a set of exact quantum steps that the molecule is willing to climb and unwilling to climb, no matter how much you wish it would behave continuously. Why light is such a perfect probe. Earlier, we leaned on a gentle truth. Energy isn't a smooth ramp in the microscopic world. It comes in steps, levels, allowed values. Light is built for that world. A single photon carries a discrete packet of energy, not some energy, a specific amount proportional to its frequency. Change the color, change the frequency, and you change the photon's energy. So, when you shine light of many colors on molecules, you are essentially offering them a menu of energy packets. And quantum systems love menus. A molecule can only accept the packets that match its allowed transitions. Those jumps between quantized states that its electrons and nuclei are capable of making. Everything else passes through, or scatters off, or simply goes unclaimed. That's the core reason spectroscopy works. Light arrives in quantized units, and molecules only accept what fits. Not because they're picky in a human way, because quantum rules are picky by nature. The molecule is a set of ways to move. Here's a useful way to feel this. A molecule is not just atoms stuck together. It's also a set of internal motions. Electrons shifting between orbitals, bonds stretching and compressing, angles bending. the whole molecule rotating in space, larger vibrations that ripple through the structure, and each of these motions has its own ladder of quantized energy levels. If you could stand inside a molecule, which you can't, but you can imagine, you wouldn't hear a constant hum. You'd hear a choir of discrete notes, specific pitches, specific harmonics. Spectroscopy is what happens when light plays the keyboard and the molecule responds by vibrating, rotating, or rearranging its electrons. Only at the notes it's allowed to hit. So, when you see a spectrum, a series of lines or peaks, you are looking at those allowed notes. You're not looking at a picture of the molecule. You're looking at its rules. Absorption. Taking a step up. Let's begin with the simplest interaction. A photon arrives. If its energy matches the gap between two allowed states, the molecule can absorb it. That absorption promotes the molecule into a higher energy state. Depending on the photon energy, that state might be a rotational state, tiny energy gaps, a vibrational state, medium energy gaps, an electronic state, larger energy gaps, and because those energy gaps are quantized, the absorption happens at specific frequencies, specific colors, or wavelengths. That's why absorption spectra have structure. Not because the experiment is fancy, because the molecule is structured. Absorption is the molecule saying, yes, that step is allowed. No, that step is not. And the pattern of yes and no becomes a signature. Emission, stepping back down, but molecules don't like to stay excited forever. When a molecule drops from a higher energy state to a lower energy one, it can emit a photon. That emitted photon carries away the energy difference. So emission spectra also contain lines, sometimes at the same positions as absorption lines, sometimes shifted depending on details like relaxation processes. Think of it this way. Absorption is the molecule catching a photon like a rung on a ladder. Emission is the molecule letting go and releasing a photon as it settles. Some emission is fast, fluorescence. Some is slower, phosphorescence. Some is complicated by collisions, environments, solvents, and surfaces. But the skeleton is always the same. Quantum states, energy differences, photons as the accounting system. Why spectra are fingerprints. Now for the most satisfying part. If you measure a spectrum, you can often identify a molecule without ever seeing it. Because a spectrum doesn't just tell you energy levels exist. It tells you which ones exist, how far apart they are, and how strongly the molecule interacts with light at each transition. That depends on the masses of the atoms, affects vibrations and rotations, the bond strengths, affects vibrational frequencies, the electron distribution affects which transitions are allowed, and the symmetry of the molecule affects selection rules. The environment shifts and broadens features, so two different molecules can have spectra that look as different as two fingerprints. Even molecules that are chemically similar, say two different alcohols, often have distinct infrared patterns, distinct rotational constants, distinct electronic transitions. In practice, spectroscopy becomes a kind of reading. You learn the alphabet. Certain peaks correspond to certain bond stretches, certain groups, certain electronic structures. And then you start recognizing words. A carbonyl group has a recognizable infrared feature. An aromatic ring has its own pattern. An OH stretch has a characteristic shape. And you realize that chemistry is not only built from atoms, it's built from vibrations, and those vibrations speak. A gentle taxonomy, different kinds of spectroscopy. We don't need to list every technique in the world, but it helps to feel the logic of why there are different flavors. Because the molecule has different ladders. Rotational spectroscopy deals with the molecule spinning in space. Tiny energy gaps, often in the microwave region. Very precise for determining bond lengths and molecular geometry in gases. Vibrational spectroscopy deals with bond stretches and bends, mid-range energy gaps, often in the infrared, incredibly useful for identifying functional groups. Electronic spectroscopy deals with electrons jumping between orbitals, larger energy gaps, often invisible and ultraviolet. This is where color lives, why some molecules look red or blue or absorb UV. And then there are variations that feel like clever extensions. Raman spectroscopy, using scattered light to probe vibrations. NMR, using radio frequencies and magnetic fields to probe nuclear spins. Still a kind of spectroscopy, still quantized transitions. Photoelectron spectroscopy, mass spectrometry with spectroscopy-like interpretation, and so on. The point isn't the catalog. The point is the theme. Light and electromagnetic radiation more broadly lets us interrogate quantized structure, its measurement, but gentle measurement, a question asked in photons. The selection rules, why some notes are silent. Here's a subtle thing that makes spectroscopy feel even more like quantum law. Not every energy gap produces a spectral line. A transition can be energetically possible. There may be two states separated by a certain amount, and yet the molecule may still refuse to absorb or emit light for that transition. Why? Because quantum mechanics doesn't only care about energy. It also cares about how the system's wave functions overlap, and whether the transition obeys certain symmetry constraints. These are called selection rules. They're the reason some transitions are allowed, and others are forbidden, or extremely weak. And forbidden doesn't mean impossible. It often means improbable, so rare that it barely appears unless conditions are special. Selection rules are why spectra have character. They shape which lines are bright and which are faint. So spectroscopy isn't just a ruler measuring energy gaps. It's also a test of symmetry and structure. A molecule revealing not only what energies it can have, but how it is permitted to change. The emotional core, spectra prove chemistry is quantum. It's easy to say, chemistry is quantum, and let it float by like a slogan. Spectroscopy pins it down. Because spectroscopy is what you see when nature refuses to be continuous. If energy were truly smooth, if molecules could absorb any amount, then spectra would be bland. You'd get broad, featureless absorption. But instead, even in messy real-world conditions, you still see structure, peaks, bands, distinct edges. Even when lines broaden due to temperature, collisions, and environments, the underlying quantization leaves its mark. It's the difference between a staircase and a ramp. A ramp gives you no information about where the steps were supposed to be. A staircase leaves a pattern, and spectroscopy is the pattern. A measurement moment you can almost feel. Imagine holding a simple object, something you take for granted. A glass of water. You would never guess that inside that water, each H2O molecule has a whole set of vibrational modes. Symmetric stretch, asymmetric stretch, bending mode. You would never guess that the OH bonds are not static sticks, but quantum oscillators with quantized excitations. You would never guess that in the right experiment, the water molecule can be recognized by how it responds to infrared light, by the exact frequencies it absorbs. Now imagine shining a careful beam of light through that water. Not bright, not dramatic, just enough. And the water answers, not with sound, not with visible motion, but with absorption at specific frequencies. It's as if the molecule is saying, I can move like this. I can't move like that. Offer me this exact energy, and I'll take it. Offer me almost the same energy, and I'll let it pass. That's why spectroscopy is such a satisfying bridge between the abstract and the real. It turns the quantum into something measurable, not in an exotic accelerator, in a lab on a bench, sometimes in a handheld device. Spectroscopy and reaction pathways. Now, let's connect this to something we've already been holding, reaction landscapes. If reactions involve passing through transition states, fleeting configurations that reshape electron density, then spectroscopy becomes one of the best ways to watch chemistry happen. Because as bonds form and break, energy levels shift, vibrational frequencies change, electronic transitions shift, new peaks appear, old peaks fade. So, spectroscopy can be used not only to identify molecules, but to track reactions over time, to infer intermediate species, to detect changes in bonding, to see when a catalyst is binding, when a substrate is activated, when a product is forming. In other words, spectroscopy is one way we observe the landscape, even if we can't walk on it directly. We look at the signatures and deduce what the terrain must have been like. Why chemists love fingerprints more than pictures. It might sound strange, but chemistry often trusts fingerprints more than photographs. Because molecules are small enough that a picture is rarely straightforward. But a spectrum is a direct consequence of quantum structure. It's like listening to a musical instrument. You can't always see the wood grain or the inside shape, but you can hear a violin. You can hear a trumpet. You can hear the difference. Spectroscopy is hearing molecules. And the reason you can trust it is that the molecule cannot fake its allowed transitions. The peaks are not opinions. They are constraints, a gentle recap that stays light. So if we gather this softly, light comes in discrete packets. Molecules have discrete energy levels, rotational, vibrational, electronic. When photon energy matches an allowed gap, absorption happens. When excited states relax, emission can happen. The pattern of allowed transitions becomes a spectral signature. Selection rules and symmetry shape which transitions appear strongly. Spectroscopy is the practical proof that chemistry is built on quantum steps. And somewhere in the middle of all that is the quiet miracle. You shine light and matter answers. A calm handoff toward the next idea. Once you accept that molecules have quantized habits, it becomes easier to accept something even bigger. Because individual orbitals don't just belong to isolated atoms. When atoms come together in a solid, those orbitals don't stay neatly separate. They spread out, blend, and form collective structures. Wide ranges of allowed energies instead of isolated lines. Not a single ladder, a whole band. And in that band structure, you begin to understand why some materials conduct electricity like rivers, and others hold it back like stone. Why some are metals, why some are insulators, and why a few sit in the middle, sensitive, tunable, quietly responsible for the modern world. If you've ever held a piece of metal and felt it run cold through your fingers, you've already met quantum chemistry in its most practical disguise. Because that coolness isn't just temperature, it's a clue. Metals share heat and electricity with a kind of effortless generosity, as if the energy you give them can flow through the whole object without getting stuck. Glass doesn't do that. Rubber doesn't. Dry wood doesn't. And silicon, quiet, unremarkable silicon, does something stranger. It sits right on the edge. It's not a carefree conductor, and it's not a stubborn insulator. It's something in between, something that can be persuaded. That in between is where the modern world lives. And the reason these materials behave so differently is not a surface level property. It's not about shininess. It's not even mostly about what atoms you used. It's about what happens to orbitals when you stop thinking in terms of a single atom and start thinking in terms of a crowd. When orbitals stop being private. Earlier, orbitals were described as allowed shapes of probability, habits an electron is permitted to have around a nucleus. In an isolated atom, those habits are neatly separated, discrete energy levels, clear steps. But a solid is not an isolated atom. A solid is an enormous assembly, trillions upon trillions of atoms arranged close enough that their electron clouds begin to notice one another. And when quantum systems notice each other, they don't stay simple. Here's the gentle trick solids play. When you bring two atoms close together, their orbitals overlap. Because electrons are quantum objects, the combined system can't keep the exact same energy level for both electrons in the same way. The energies split, one slightly lower, one slightly higher, so the overall wave function can obey the rules. Now imagine not 2 atoms but 10. More splitting, 100, more, 1 billion. At that scale, the energy levels stop looking like separate rungs. They become so densely packed that they form a near continuum, bands of allowed energies. So, a band is not a brand new quantum idea. It's the same orbital logic, just multiplied until it becomes smooth to our eyes. A solid is what you get when individual quantum steps blur into a wide, collective range of possibilities. Allowed bands and forbidden gaps. Once you accept the idea of bands, the next idea follows almost automatically. If there are ranges of energy that are allowed, bands, There can also be ranges that are not allowed. These are the band gaps. Think of it as a city map drawn in quantum ink. There are neighborhoods where electrons are allowed to live, and stretches of land where they simply cannot exist in stable states. That's a band gap, a forbidden zone between two allowed neighborhoods. And now, we're close to the reason materials divide into three familiar personalities: metals, insulators, semiconductors. They're not different because of vibes or textures. They're different because of where the electrons sit relative to the bands, and how hard it is to move them into a state where they can roam. The valence band and the conduction band. To keep it intuitive, solids are often discussed using two main bands. The valence band is the band filled with electrons that are bound up in the material's bonding structure. Electrons that largely stay tied to atoms and bonds, doing the quiet work of holding the solid together. Above that is the conduction band, a band of states where electrons can move more freely through the lattice, contributing to electrical conduction. Between them may be a band gap. So, conduction is not electrons flying loose in a cartoonish sense. Conduction is electrons occupying states that let them respond to an electric field by shifting their momentum through the crystal in a coordinated, collective way. It's not chaos, it's permitted motion. And the difference between a conductor and an insulator often comes down to one question. Is it easy for electrons to reach the conduction band? Metals, the easy flow world. In a metal, electrons have available states right near where they already are. Often the valence band is partially filled, or it overlaps with the conduction band. There's effectively no meaningful barrier to motion. So, when you apply an electric field, electrons don't need to jump a large gap. They can slide into nearby available states and begin to drift through the lattice. Not fast like bullets, drift is slow, but with a collective response that transmits electrical influence quickly. This is why metals conduct so well. Not because electrons are unbound in a dramatic sense, because the band structure provides a dense supply of nearby allowed states, and the electrons can shift into them with almost no energetic cost. A metal is a material where quantum permission is generous. Insulators, the locked-up world. In an insulator, the valence band is full and the conduction band is empty, with a large band gap in between. A full band is important. If all the nearby states are already occupied, the electrons can't easily rearrange their motion in response to an electric field. There's no room to move without breaking the rules. And the gap makes it worse. To create conduction, you would need to supply enough energy to promote electrons across the forbidden zone into the conduction band. If the gap is large, ordinary thermal energy at room temperature isn't enough, not even close. So the electrons remain in the valence band, bound into the structure, and the material resists conduction. An insulator is a material where quantum permission is strict. Semiconductors, the quiet edge case. A semiconductor sits between those extremes. Like an insulator, it typically has a full valence band and an empty conduction band. But unlike an insulator, its band gap is small enough that electrons can sometimes be promoted into the conduction band with modest energy, heat, light, or an applied voltage in the right context. That small gap changes everything. Because now the material is not permanently locked, it's conditionally unlocked. A semiconductor can be coaxed into conducting, not always, not effortlessly, but controllably. And controllability is more valuable than raw conduction. That is the soft secret behind silicon's power. It's not the best conductor. It's not the best anything. It's simply the most obedient when you ask it to switch. The missing partner, holes. If an electron gets promoted from the valence band into the conduction band, it leaves behind an empty state in the valence band. That vacancy behaves like a positive charge carrier, because electrons in the valence band can shift around to fill the vacancy, making the vacancy move in the opposite direction. This is called a hole. A hole is not a particle in the same way an electron is. It's an absence. A bookkeeping trick that becomes physically useful because many electrons moving collectively can be described more simply as one hole moving. In semiconductors, both electrons in the conduction band and holes in the valence band can contribute to conduction. So The conduction story becomes a duet. One carrier is matter, one carrier is missing matter, and both are real in their effects. Doping, gentle persuasion, not brute force. Here's where semiconductors become unmistakably modern. In pure silicon, there are some thermally excited electrons and holes, but not many. The material conducts a little, but it's not impressive. So we cheat politely. We add tiny amounts of impurities, dopants. Not enough to change the overall structure drastically, just enough to tilt the balance of carriers. If we add an atom with one extra valence electron compared to silicon, like phosphorus, we create N-type material. It contributes extra electrons that can more easily enter the conduction band. If we add an atom with one fewer valence electron, like boron, we create P-type material. It creates more holes, more vacancies that behave like positive carriers. This is not messy chemistry, it's precision, it's micro-scale negotiation. Doping is basically saying, I want the same crystal, but with a slightly different electron economy, and the economy changes the material's personality. The junction, where switching becomes possible. When you bring P-type and N-type materials together, you form a p-N-s junction. At the junction, electrons and holes diffuse into each other's territory and recombine, creating a region depleted of mobile carriers. That depletion region acts like a barrier. In one direction, it's easy to push carriers across. In the other direction, it's difficult. So a p-n junction can act like a one-way valve for current, a diode. But even more importantly, junctions can be combined and shaped into transistors, the basic switching elements in computers. A transistor is not magic. It's a controlled manipulation of band structure and carrier populations. It's the ability to create, widen, narrow, and redirect the region where electrons are allowed to move. And that is a very quantum form of control. Why LEDs glow, a band gap with a color. There's a reason semiconductors show up not only in computers, but in lights. When an electron in the conduction band recombines with a hole in the valence band, energy is released. Sometimes that energy becomes heat. Sometimes, if the material is the right kind, it becomes a photon. The energy of that photon is related to the band gap. Small band gap, lower energy photons toward infrared. Larger band gap, higher energy photons toward visible light, and then into ultraviolet. So an LED is a device that turns band structure into color. It's not a warm filament glowing from heat like an incandescent bulb. It's a quantum process. Electrons falling across a gap and releasing a specific packet of energy as light. In a calm way, it's spectroscopy in reverse. Earlier, you shined light and matter answered by absorbing. Here, you provide electrical energy and matter answers by emitting. And again, the answer comes in quantized truth. Why bands are not just an electronics topic. It can be tempting to treat band theory like a detour into engineering, but it's still quantum chemistry at its core, because the bands come from orbitals, from overlap, from the same wave nature that makes bonding possible. A solid is chemistry scaled up until the energy landscape becomes collective. And once you see that, everyday categories start to feel less like labels and more like outcomes. Metal becomes has available states for motion. Insulator becomes has a large forbidden gap. And semiconductor becomes has a modest gap and controllable carriers. These are not different substances in spirit. They're different solutions to the same quantum rules. A quiet moment of perspective. Why solids feel solid. There's another gentle comfort hidden in this. Solids feel stable and solid to us, but at the microscopic level, they are an organized choreography of quantum states. Electrons spread across many atoms, occupying bands that are less like little marbles and more like shared patterns. The hardness of a material isn't about atoms being packed like stones. It's about allowed states, filled bands, repulsive forces, and the way a lattice resists deformation because disturbing it means disturbing an enormous coordinated quantum arrangement. Solidity is not brute force, it's structure. The kind of structure that quietly returns to equilibrium when you try to push it out of place. Thermal effects, why temperature matters. Temperature adds a gentle agitation, more phonons, more vibrations in the lattice. Those vibrations can scatter electrons, affecting conductivity. In semiconductors, heat can also promote more electrons across the band gap, increasing the number of carriers. That's why semiconductor conductivity often rises with temperature, unlike metals, where conductivity usually decreases because scattering increases. So even temperature becomes readable in band language. The solid is not static. It's a living lattice of quantized motion, electronic and vibrational, from orbitals to a civilization. If you zoom out just a little, this is the astonishing arc. Orbitals, probability habits around one nucleus, become shared states across trillions of nuclei. Those shared states become bands. Bands create gaps. Gaps determine how a material behaves with electricity and light. And that behavior becomes the foundation of radios, phones, computers, satellites, medical scanners, LEDs, solar panels, and the quiet glow of screens lighting up bedrooms at night. All of it built on the simple idea that electrons are not free to do anything they want. They live inside permission, a soft bridge toward computation without forcing it. And there's one more reason band theory matters for where we're headed. Because the moment you start describing solids with bands, you are already doing a kind of calculation. You're already making approximations, building models, deciding what to ignore and what to keep. Even the clean story, valence band, conduction band, band gap, hides a mountain of quantum detail. The true many electron problem in a real material is vast. The lattice is huge. The interactions are many. The wave functions are collective, and yet we still manage to predict, design, and engineer materials with incredible accuracy, not by solving everything exactly, but by finding the right level of description, usable shadows that still track reality closely enough to build a world from. That's where the next idea naturally waits, the computational tools we use to make quantum chemistry practical, and the careful compromises that make those tools possible. There's a point in every science story where the room gets too crowded. Up to now, quantum chemistry has felt almost elegant. Energy levels like steps, orbitals like allowed habits, bonds like agreements, light asking questions and molecules answering back. Even solids, with their bands and gaps, still feel like a clean extension of that same logic. But then you try to do the thing a chemist actually wants to do. You try to predict, not in a poetic way, like this should probably bond, but in a precise way. You want numbers, you want a structure, a reaction barrier, a spectrum, a binding energy. You want to know what happens if you swap one atom for another. You want to design a catalyst that nudges a reaction faster without breaking the product. You want to know where the electron density will gather, where it will thin out, where it will resist being moved. And the moment you ask for that level of certainty, the room fills up with electrons. A lot of them, and electrons, as you've probably learned by now, do not like to be ignored. The problem that explodes quietly. Here's the gentle truth, hiding behind most quantum chemistry. The exact Schrödinger equation for a real molecule, many electrons, many nuclei, can be written down. That's not the hard part. The hard part is solving it. Because every electron interacts with every other electron. Their positions are linked, their motions are tangled. The wave function isn't a neat little object you can sketch. It's a vast mathematical creature that lives in a high-dimensional space. One electron has a wave function in ordinary space. 2 electrons? The wave function lives in a space with twice as many coordinates. 10 electrons? It's already enormous. 100? It's beyond anything you'd ever want to hold in your hands, even as math. This is why quantum chemistry feels like a miracle. The world runs on the exact rules, and we almost never solve them exactly. So instead, chemistry learned to do something very human. It learned to compromise, not sloppily, strategically. It learned to build models that keep the important quantum truths while letting the impossible details fade into the background. The first compromise: we can't track everything. If you had infinite computational power, you could, in principle, calculate everything about a molecule from the fundamental equations, every energy level, every vibration, every electron distribution, every reaction pathway. But in practice, the exact approach grows too fast. It doesn't grow like a straight line. It doesn't even grow like a steep hill. It grows like a cliff. As systems get larger, the computational cost often scales in ways that become brutal. The number of interactions, the complexity of electron correlation, the size of the basis sets you need to describe the electrons. The effort can balloon from hard to impossible, with what feels like a small increase in molecular size. So quantum chemistry, almost from the beginning, asked a calmer question. What can we compute that still tells us the right story? Not the full story, the right one. The big pivot, stop chasing the wave function. This is where one of the most influential ideas enters the scene, quietly, like it was always meant to be there. Density functional theory. DFT's central move is almost philosophical. Instead of describing a molecule by its full many-electron wave function, DFT describes it by something simpler, something closer to what you could imagine measuring. The electron density, how the electronness is distributed throughout space. A density is a function of 3 coordinates. It tells you, for each point in space, how much electron probability lives there. And that's a dramatic simplification. The many-electron wave function is a function of an absurd number of coordinates. The density is a function of ordinary space. So, DFT is the art of trading an impossibly detailed description for a more compact one, while still being able to recover the energies and properties we care about. It's like saying, I don't need to know every conversation in the stadium. I need to know where the crowd is cheering. And somehow, this is the part that feels like magic. Theorems and the foundations of DFT tell us that the ground state energy of a system is determined by its density. Not by the full wave function, at least not explicitly. By the density, that single fact reshaped quantum chemistry, the catch that never goes away. But there's a delicate wrinkle. DFT promises that the exact answer is, in principle, encoded in the density. Yet the method still requires an ingredient we don't fully know how to write in perfect form. The exchange correlation in functional, the part that accounts for the subtle many-electron effects that arise from quantum statistics and electron-electron interaction. So DFT is powerful, but it comes with an unavoidable reality. To do DFT in practice, you must choose an approximation for that functional. And the moment you choose an approximation, you step into the world of trade-offs. The triangle of trade-offs: accuracy, speed, usefulness. Nowhere here's the quiet tension underneath most computational chemistry. You want results that are accurate enough to trust. You want them fast enough to run. You want them broadly useful across many kinds of molecules and materials. But you rarely get all 3 at once. Some methods are beautifully accurate, but too slow for large systems. Some are fast but not reliable in tricky cases. Some work well for one class of molecules and fail strangely for another. So, computational chemistry becomes a kind of navigation. You're not only computing, you're choosing a path through a landscape of approximations. And the best practitioners are not the ones who always pick the most sophisticated method. They're the ones who know where a method breaks, where it stops being a faithful shadow and starts becoming a misleading one, a soft picture, what DFT is really doing. Imagine a molecule as a landscape of charge and attraction. Nuclei are heavy anchors of positive charge. Electrons are a cloud that can gather, stretch, thin out, form bridges, create barriers. DFT tries to settle that cloud into the lowest energy arrangement, the most stable shape it can take, given the positions of the nuclei. From that settled density, a remarkable amount can be inferred. Where bonds will form and how strong they are. Which regions are electron-rich or electron-poor. How a molecule might react. How it will interact with light. How it might behave as a solid, a semiconductor, a catalyst surface. That's why DFT shows up everywhere. In drug design, materials, science, batteries, catalysts, solar cells, semiconductors, and more. It's the workhorse method of the quantum chemistry world. Not because it's perfect, because it's possible. Why approximation doesn't mean guess. This matters for the tone of the story. When people hear approximation, they imagine a shrug. But in quantum chemistry, approximations are often carefully engineered compromises backed by huge bodies of benchmarking and experimental comparison. They aren't random guesses. They're more like lenses. Some lenses are good for landscapes, some for portraits, some for night skies. If you use the wrong lens, you don't just get a slightly blurry photo, you get the wrong scene. So an approximation is a tool with a personality. And a good computational chemist is someone who knows those personalities well enough to trust them without worshiping them. The first unsettling question: what are we really calculating? And now, right on schedule, we arrive at a question that has the same viral flavor as the strongest competitor moments. Because it's simple, and it's slightly uncomfortable. When we do computational quantum chemistry, what are we actually calculating? Are we calculating reality, or are we calculating a usable shadow of reality? The temptation is to say reality because the numbers can be incredibly accurate. Sometimes DFT predictions match experiments closely. Sometimes it helps design materials that actually work. Sometimes it tells you about a reaction barrier before anyone measures it. That feels like reality, but the deeper you look, the more you notice a subtle truth. We are not simulating the universe molecule by molecule perfectly. We are constructing a mathematical representation that captures what matters most for the question we're asking. And that representation depends on choices: which functional you use, which basis set you choose, whether you include dispersion corrections, how you treat solvent, how you handle temperature or vibrations, whether you treat electrons as more localized or more spread out, whether you assume a certain spin state or symmetry. Each choice is a statement, not about what the universe is, but about what we are willing to ignore to make calculation possible. So, the answer is calm and honest. We calculate something real because the world answers back when we test it. But we also calculate something shaped because we cannot afford the full complexity of the exact problem. A usable shadow can still be faithful, but it's still a shadow. The second question: where do approximations break? Here's another question that sounds almost like a warning, but it's really a guide. Where do approximations fail? And can we tell when they're failing? This is the heart of responsible computational chemistry, because models don't usually fail by raising a red flag. They fail quietly. They give you a plausible number with the wrong confidence. So, you learn the classic danger zones, systems with strong electron correlation, where electrons are deeply entangled in behavior and can't be captured well by simpler descriptions. Transition metal complexes, where d electrons can behave in ways that are delicate and method-dependent. Reaction barriers that depend on subtle balance between competing electronic states. Weak interactions, like van der Waals forces, where certain functionals historically struggled without corrections. Charge transfer states and excited state chemistry, where ground state methods may mislead. And the interesting part is this: you often detect failure not by a single run, but by cross-checking. You compare different functionals. You compare different levels of theory. You check whether the result is stable to small changes in the setup. You ask if the answer makes chemical sense. You validate against experiments when possible. In other words, you treat computation like science, not prophecy. And this brings a kind of comfort. The field knows its limitations. It lives inside them. It doesn't pretend they aren't there. The third question: will quantum computers change chemistry? Now, the final question, the one that almost feels inevitable in a channel called the Quantum Slumber. Will quantum computers revolutionize chemistry, or only certain parts of it? It's tempting to imagine a future where a quantum computer simply runs the exact Schrödinger equation for huge molecules, and all approximations vanish. But even that dream has nuance, because quantum computing isn't a magic fast button. It changes which problems might be tractable and how they scale. Some of the hardest parts of quantum chemistry, accurately modeling electron correlation in large systems, are natural targets for quantum algorithms. In principle, a fault-tolerant quantum computer could represent quantum states more directly than classical computers can. That's the promise. But there are also constraints. Real large-scale quantum computers with low error rates are still extremely challenging to build. Many chemical problems are not just about electrons. They involve nuclear motion, solvent effects, temperature, and messy real-world conditions. Even with quantum computers, you may still want approximations because exact isn't always necessary for a practical decision. So the likely future isn't classical dies, quantum takes over. It's more subtle. Quantum computers may become specialized tools that handle certain bottlenecks. Specific electronic structure tasks where classical methods struggle, while classical computing and approximate models remain essential for scale, speed, and integration with real-world chemistry. In other words, quantum computing might not replace the art of approximation. It might change where the boundary sits. It might push the cliff farther away. A gentle synthesis, the courage to compute imperfectly. If there's a quiet moral to this section, it's this. Quantum chemistry works in the real world, not because we always know the exact truth, but because we know how to ask questions the world will answer. DFT is a method built from humility. It admits the full many-electron problem is too large, and then it offers a way forward anyway. It says, we can compute the density, we can compute energies, we can make predictions, we can design, we can build. Not perfectly, but well enough to shape reality. Chips, catalysts, medicines, batteries, materials, using quantum rules as the hidden architecture underneath. And that's almost the most human thing quantum chemistry ever did. It took the most exact theory we know, and learned how to live with its complexity without surrendering to it. So if you ever feel that approximation sounds like weakness, it may help to reframe it. In quantum chemistry, approximation is not failure. It's how we make the invisible usable. And in a world as deep as electrons, that's a kind of quiet strength. Because the point was never to compute everything. The point was to compute enough of the truth to let matter, once again, show us what it can become. If you've stayed with me this long tonight, you've already felt the strange little flip that quantum chemistry gives you. At the start, chemistry can look like a catalog of substances and reactions, powders, liquids, crystals, smells, colors, a world that seems solid and continuous. But underneath that familiar surface, everything is being quietly governed by rules that come in steps, not smooth slides. Allowed energies, allowed shapes, allowed ways to share electrons. Even when matter looks still, it's being held together by something more, like a set of permissions than a set of parts. And once you notice that, the everyday world starts to feel a little different. A coffee mug isn't hard in the way it feels. It's a stable arrangement, an agreement, between electrons and nuclei, between attraction and exclusion, between standing waves and boundary conditions. A sheet of metal isn't just metal. It's a crowd of quantum states filled up to a certain level, leaving just the right freedom for electrons to drift when you push with a voltage. A piece of glass isn't simply see-through. It's a material whose allowed energies refuse to absorb most visible light, so the photons pass through like unanswered questions. Even that word solid starts to soften. What feels like a final, stubborn surface is really a choreography of probabilities. Not random, never random in that sloppy way. More like quiet precision. The kind that's so consistent you can build the entire modern world on top of it, and never once have to see the equations to trust that they're there. That's the hidden architecture we've been circling tonight. Energy levels that turn atoms into instruments with specific notes. Orbitals that behave like the allowed habits of electrons. Bonds that aren't little hooks, but shared patterns. Overlaps, symmetries, compromises. Reactions that move across landscapes, choosing paths that look like the easiest climb. Light that interrogates matter, and matter answering back in a spectrum. Clean, specific, unmistakable. Solids that transform those same orbital rules into bands, and bands into conductors, insulators, and semiconductors. And then computation, our human attempt to sketch the outcome of all that complexity with models that are useful, even when they aren't perfect. And if there's a single gentle takeaway, it's this. Chemistry isn't a separate layer added on top of physics. Chemistry is what quantum physics looks like when it's wearing everyday clothes. It's quantum rules, softened into substances. Quantum rules, translated into smell and color and temperature and taste. Quantum rules, disguised as the ordinary. That can feel almost poetic if you let it, because it means that the world around you, your room, your sheets, the air you're breathing, has a kind of quiet mathematical integrity. Not cold, not distant, just steady, reliable, patient. The same rules holding a hydrogen atom together are the ones shaping the molecules in your bloodstream and the proteins in your cells and the minerals in your bones. It's all the same architecture, repeating, scaling, nesting. And if you're listening late at night, maybe that steadiness is the point. You don't have to solve the equations to feel the comfort of the idea that beneath the noise of the day, beneath the headlines and the inbox and the to-do lists, there's a deeper order that doesn't rush, a set of rules that doesn't panic, a reality that keeps its promises. If you want, take a slow breath and let that be the last thought that really lands tonight. Matter isn't solid, it's composed. Not just assembled, composed like music, notes and harmonics, allowed patterns. A calm set of constraints that make the world possible. And before we close, a very soft reminder. If you enjoy these slow, late-night science journeys, you can gently tap, like, and subscribe. It helps this channel find the other night owls out there who need something quiet and thoughtful to fall asleep to. And if you feel like it, leave a comment telling me where you're listening from and what time it is in your corner of the night. I always love seeing how far this little calm signal travels. All right, no rush from here. Let your shoulders drop a little. Let your jaw unclench if it's been holding on without you noticing. Let your eyes do whatever they want. Heavy, half closed, fully closed. You don't need to keep up now. You've already done the curious part. From here, you can simply drift. And as you drift, it might be comforting to imagine the world continuing on in its quiet quantum way. Electrons settling into their allowed spaces, energy stepping only where they're permitted, bonds holding gently, light moving through the dark, matter staying composed. Thank you for spending this time with me. Good night, and I'll see you in the next slow journey. Sleep well.